Okay, welcome back to Particle Physics and the Standard Model. This is lecture 26, and as you can see here, in the previous lecture we constructed the Dirac equation, which is the equation of motion for spin half states, correct? And to do that we try to linearize the special relativity equation or try to linearize the Klein-Gordon equation, if you want to put it that way, and saw that forced upon us certain matrices that had some special properties like this, right? And there were any number of bases that you could have chosen for these matrices, and we are going to work in the wild basis. Whatever be the case, we ended up getting a nice simple looking, one of the most important equations in physics, the Dirac equation, right? And of course we know better than Dirac himself now not to interpret the psi as a wave function, but as a quantum field, just like any other quantum field. So it is also a quantum operator that can create and annihilate particles in Fock space. Good. And then this is where we realized that the psi field should be written as a 4 element column matrix, because the gamma matrices, the smallest set of gamma matrices that work to satisfy these conditions are 4 by 4. So since I am hitting it with the gamma matrix, I need it to be a 4 element column matrix. And then I promised you that certain structures that we see here, like the fact that they break up into 2 by 2 blocks and then they remind you of quantum mechanics spinors, they all come from Lorentz invariance, right. So from this lecture onward we are going to see how all this comes about, and to get there let us first, what do we do after we write down the equation of motion? We solve that equation, right. So let us first solve the Dirac equation and see what physical meaning we can infer from the solution, okay. Very good. Now I am not going to write down the full plane wave solutions, okay. Notice that I already said plane wave, because what else could it be? When we are talking about a free theory, even in Klein-Gordon we got a plane wave, right. Even for spin 1 we got plane wave. So of course you are going to get some plane wave solution, but the full solution in all its glory, that is not something I am going to derive here, okay, because it is not terribly illustrating. For that I am going to refer you to Griffith's section 7.2, basically chapter 7 section 7.2, okay. But of course this is a simple enough equation, it is just some matrices, you can solve this yourself, okay, it is not that hard at all, alright. Maybe you can use some code like Mathematica to help you see how the solution comes about, but you can solve it yourself, okay. What I will do here is, so here is I am going to get a static solution. What that means is I am going to get a solution in this frame, okay, where the 3 momentum is 0. What does that mean? What should I do here in this equation? How should I write the Dirac equation? I should just get rid of the spatial components, that is it. So I am just going to write the Dirac equation as, in this frame, just the 0th component, okay. So what is the solution? Do not forget that psi is a 4 cross 1 matrix, okay. So with that in mind I am going to just write a solution like this, and I hope you will agree this comes about again from the fact that the gamma 0 can be broken down into 2 by 2 blocks, gamma 0 is the one is here and the other one is here, okay. So that I can now write the solution in terms of the psi A and the psi B, okay. They both are what? 2 cross 1, 2 cross 1 matrices, right. So that I get a totally a 4 cross 1 matrix. So let me put it this way. Actually, let me still keep writing equations as opposed to the solution right away. Once I recognize that I can write psi like this, it makes life a bit simpler. That would just mean now that the equation becomes I partial t psi A equals m, what is this now, psi A or psi B? It has to be psi B. That is just what the gamma 0 matrix does, okay, in the wild basis at least, right. And similarly, partial t with psi B will give me m psi A, okay. Good. This is what we are going to solve, okay. So what is the solution? The solution becomes easier to see if we now slightly rotate the basis, okay, and go to a basis where I can define a psi alpha as psi A plus psi B over 2 and psi beta as psi A minus psi B over 2, okay. Then what happens? Then the equation looks a little more easy to solve, right. Now the plane wave solution is even more visible, right, because the solution now looks like this. As a function of time, this is just e power I m t with whatever the initial condition is, and the other one is e power minus, because that equation had a minus on the on one of the sides, right. Okay, that is the solution, okay. Now again let me point out, just written this way, right, this looks like a solution with a negative energy state, looks like a state with negative energy. That is absolutely not what you should do. You should not interpret this, okay. So this is not a quantum state, it is not a quantum state as such, evolving as e power minus e t over h bar, okay. That is not what it is, it is not a state, okay. This is the operator actually, right, okay. Then you will not go wrong, just antiparticles with positive energy, okay. So we have now written down, this is also what, this is also 2 by 2, right, sorry 2 cross 1 actually, 2 by 1 matrices, right. So we have written all these matrix solutions now, right, 2 cross 1 matrices, everything is working out well, but it is still not clear what these things really are physically. A 4 vector we understand, right, 4 vectors arise in relativity, and people say that 4 vectors are defined as objects that transform as 4 vectors, right. So we do have an understanding of that from the Lorentz group, but now I have just started writing matrices all over the place and it is not really clear what these objects really are as far as Lorentz invariants and things like that are concerned. correct. So, what really are these psi alpha, psi beta, psi A, psi B and so on. Okay. See the psi in some basis I can now write as some psi alpha, psi beta, right. So, some other basis, literally these are, there is a spinner sitting here and there is a spinner sitting here, literally this is what it is. Okay. So, what is this object? What is this object? Why do they behave like this? Okay. So, let me give you the answer first and then I will derive it. Basically these things, okay, are the spinners of quantum field theory, not of quantum mechanics. This is where I like the word spinners. As I told you earlier, for quantum mechanics I prefer the word spinners or whatever, okay, but these are the real spinners in field theory, and they are nothing but yet another representation of the Lorentz group. Okay, absolutely nothing but yet another representation. We have already seen two representations, scalars and vectors, 4 vectors. We are going to see now that this is nothing but yet another representation, and this is the most important representation. Okay, I am going to objectively say this is the most important representation. Why? Because we are made of fermions, right. Without fermions, no matter, nothing to speak about, right. So, this is the one of the most fundamental things to learn here, okay. And most of the standard model states are spinners. Forget that we are made of fermions. Even if the standard model existed without us existing, most of the standard model states are also spinners. The quarks, right, leptons, all of them, composites like baryons, right, good. So, how do we see this? Okay. Let us take something that we already know from before. Let us take rotations. Okay. What happens under rotations? I am changing my coordinates like this, right. I can put an r, but I am going to just use lambda. I am going to start using lambda right away. I am going to call these or if you want I can preserve the index. Okay. Okay, where the lambda here, right, because this is a rotation in the yz plane, I am going to write a rotation in the yz plane. Okay. So that I can call the rotation angle some theta x, agreed. So I have cos theta x, sin theta x, minus sin theta x, cos theta x. Anything else I have not written is to be, it should be taken as a 0. Okay. And of course other rotations involving theta y and theta z. Okay. Good. Does this form part of the Lorentz group? It absolutely does. Okay. People think, generally naively people might think that Lorentz group encompasses only the Lorentz boosts. because it has the word Lorentz in it. No, the Lorentz group also contains rotations. Okay. So, this is definitely one representation of the Lorentz group. Let me write down other kinds of representations. You would also have, so let me just write, and you can also have boosts in the x direction parameterized by beta, right? Remember from your relativity course. So, boost in the x direction I can write this way, and in other directions I can write using a beta y and a beta z. Okay. So, what are these now? These are this and this, these are all nothing but some representations of the Lorentz group. What is the Lorentz group? It is SO13, right? To denote Minkowski space, you do not write SO4, you put SO13, time and 3 spatial components. Agreed? Okay. And for those who are interested, you can go check what these words mean. What I have written down in particular is an orthochronous and proper Lorentz group. Okay, I made sure that time has a positive sign and that this particular representation is connected to identity. If I take thetas and betas to 0, I get identity. Okay. But the important thing for physics is these are representations of the Lorentz group itself. Okay. Now, I do not have to always write down the full transformations this way, okay, because it turns out that if I just write the infinitesimal transformation, right, they contain the DNA of groups, basically a special kind of group particularly, but in general. Okay, so it is illustrative to see what the infinitesimal transformations look like. That is easy. Okay, I just have to take the small values. So theta, so I just, instead of sin theta, I will write delta theta. For cos theta, I will take it as 1. So I am just going to keep terms only up to linear order. That is what it means. Okay, similarly for the cos hyperbolic and sin hyperbolic functions. Okay. In that case, let us see how the spatial, I am going to put these together and see how the temporal and spatial components transform in X. Okay. The temporal component goes as what? There is only a boost on it, right? Of course, you can't rotate time, right? You can only involve boosts with time from here. Okay. And the cinch goes to 0, right? Good. And for the spatial component, what do I have? Again, look at this. Over here, the cosh is what I am taking, right? And notice that the I and the I actually, sorry, this is what I should have done. I should have put a delta 0 actually. So this I corresponds to the correct spatial component, but then you basically taken the temporal component of the coordinates themselves, right? So that is how boosts work, right? Minus for rotations, I am just going to write a shorthand, where I have this. Okay. Agreed? Now there is something I have used here already implicitly. I have used the Einstein convention for summing over repeated indices. So Einstein summation, right. So whenever you see repeated indices j and k, they are summed over basically, okay, so that we do not have to keep writing the summation sign, right. Probably Einstein's most important contribution to theoretical physics. He figured that when people look at repeating indices, they will know how to, they will know that you have to sum over them, so just drop the sigma sign. Okay. So together I can now write these two equations in one shot like this, right. I have a delta x mu, I am going to write it in a slightly odd manner, but bear with me, you will see that this turns out to be the most useful way to write it. Okay. First I am going to pull out an I, and then I am going to say that there is, this I is different, okay, this is an index. For the spatial components I have delta theta I, which I am going to hit with a matrix, okay, to represent these rotations, okay, and of course I am going to put the Lorentz index on the matrix, okay, plus k I, again I am going to put the Lorentz index on this matrix, the Lorentz indices, then I have a delta beta I, alright. So this summation works for both of these, okay, and finally of course I am transforming the coordinates, right. So I have x nu, okay. So from here and these matrices and writing this way, you can guess what the ji's and the ki's are at this point. The ji's, let me just write a j1 first. The j1 is nothing but, there is another I now thankfully, because this I and this I will cancel and you get a real number like you have up here. How did the j1 look like? There are two okay, so the diagonal entries are all 0 and I have this, agreed. Look at this, right. So here I have infinitesimally I have, this is 1, this is a -1 with a delta out and so on, correct. Of course now I pulled out an I, there are more I, so that the signs flip, but this matrix corresponds to these rotations, agreed. So if I hit it with the infinitesimal 1, you are going to get rotations around the x axis, right. So similarly, and you have j1 and j2, j2 sorry j2 and j3 obtained similarly, okay. What about the k's? Again let me write one k matrix. I have 0 -1 -1 0 0 0, okay, and similar k2 and k3, okay. These are very special matrices, okay, because this is what is called, these are what are called generators, okay. In general you will have generators for these groups. In this case these are the generators of the Lorentz group. Okay, in the 4 vector basis. I say that because we are going to see some very interesting thing coming out of this in another basis. Okay, why do I say that? Why do we say this is generator? Because using this infinitesimal transformation, remember we started by writing some generic lambda mu nu. That lambda in general could just be an exponentiated form of these transformations. Okay, so this over here. So I can just write a generic um, 4 by 4 Lorentz transformation matrix as an exponentiated form of these matrices where the 3 rotations and the 3 boosts figure, and for that I just have to hit the rotations with the relevant generator for the rotations, and I have to hit the actual amount of boost with the relevant generator for the boost. Okay, so it is intuitive, right, why it is called a generator. This generates the entire group basically. Using infinitesimal transformations you can generate the entire group. Okay. Good. So the Lorentz group actually falls into one particular classification of groups because of this property. This is what we call a Lie group. Okay, the Lorentz group is an example of the Lie group. So what is a Lie group? It just means, for the purpose of this course, you have infinite elements, right? Obviously you have infinite elements here, you can write down any number of 4 vectors, but only finite number of generators. In this case how many? Just 4, sorry, just 6, right? 6 for Lorentz, 3 boosts and 3 rotations, right? Okay. Now closely related to the Lie group is something called a Lie algebra. It is not the most important thing, but it helps us organize our thoughts on groups and representations and so on. So let me just say it, okay, and that will wrap up today's lecture. But notice that you can actually add and multiply the Ji's and the Ki's, right? Correct? In other words, the generators are in, they are not in a group really, but they are in an algebra. Agreed? Whereas the group elements right, you can only multiply them when you want to do these transformations and so on, right. So, the group elements are these, right. So, they are in a group basically, obviously, right. So, this gives rise to the notion of, since you have the generators being in an actual algebra, this gives rise to the notion of a Lie algebra. Okay. So, basically the generators form a Lie algebra, that is, there is a multiplication rule for the generators themselves. Okay. In the case of the Lorentz group, I am just going to write Lorentz group's Lie algebra, you can also call it Lorentz algebra. It looks like this. This is the algebra that the generators themselves live in, satisfy. The rotations go like this. Of course, you are familiar with that, right? But what about rotation and boost? That gives you back a boost, it turns out. Okay. And of course, another surprising thing is if you take the commutator of two boosts, right, you actually get the rotation generated. Okay. So, the first one is not surprising, but the other two look a bit surprising, right. So, this has to do with things that you might have learned in special relativity, things like let me just write the words here, go back and look at it, Thomas precession and so on, okay. And go look this up. People say that a double boost, this is what you have, right, a double boost is basically a tilted boost, okay. This is not really the place for me to explain all this, but these are very nice relativity concepts that you see encoded in the algebra itself, okay. So, let me just introduce one other term. The multiplication rule of this algebra is also called the Lie bracket, okay, multiplication rule. So, you will come across these terms in mathematical physics, field theory and so on, okay. So, let me just end this class now by saying that this Lie algebra for any group, right, for Lie groups, this is kind of the most important thing that defines the representation of the group itself, okay. This is really all you need to know to construct the, just like you know for the Dirac matrices you needed the anti-commutators, really the DNA of the representation that you are thinking of for this group is all there, is all encoded in the generators themselves. So, once you know the Lie algebra, you can work out what the generators are, and from there you can work out the entire group, okay. So, we will take this concept and turn it around in the next lecture and see if we can construct other representations of the Lorentz group, and we will see something very interesting happens, okay. So, we will do that in the next class. Thank you.